My name is Vitaly Wool, and I was doing embedded Linux stuff for a really long time. Starting from Monte Vista, doing stuff for them, primarily for Monte Vista Europe, and then consulting off of Sweden for companies like Sony and Google Access and whatnot. And while doing that, I was doing a lot of kernel stuff related to memory management and swapping as such. Recently, I was getting really into the Rust for Linux initiative and how it all gets together. And I can, since this is basically a discussion, I really don't want to follow this slide's order. I'm afraid things are real slow here, but however, I have a nice slide somewhere. No, but it's I'll go back to this. So the reason why I was fascinated by Rust is that by Rust in Linux is that I had two competing implementation of the same algorithm. And one was written in C, another was written in Rust, and they actually showed the same performance, or actually the Rust one, which was implemented exactly the same, was slightly faster, which was so surprising to me that I really wanted to go further with that. Then let me try to go directly to the slide 3. Why Rustify? So if we want to do something in Rust, if we want to move something to Rust, re-implement something that's there in the kernel in Rust, so why would we do that? So there's a bunch of reasons, primarily related to memory safety and security and maintainability and documentation. There are stricter coding rules and stricter standards on providing documentation for new Rust code. And then you basically get a lot of documentation pretty much for free by generating what's in there already in the code as a part of the submission. And that's all good, that's all fine, but I was often challenged by the question, well, you're going to lose some performance by doing this. And at least in my experience, I don't see that. So there are reasons to do things in Rust. We need to take those with a pinch of salt. But however, there are things that are working really great there. And the things that assumed to be not so well working, they are improving. So there is definitely a value in rewriting things in Rust, which the things that are maybe not exactly up to the point right now. So kernel swapping. So we have generic swap structure. If we talk about kernel swapping, the bird fly view, generic swap structure. Then there are some helpers or optimizers, like various RAM-based compressed swap caches or storages. And those have front ends like zswap, the compressed write-back cache, and zram, which is like a fake block device with compression. And to a certain extent, we can name shared memory as HMEM also part of the swapping structure, because it's instrumental, for instance, for GPU drivers, because GPU drivers use it for page swapping. And if we take a look at this structure, then the question is what we can and what we cannot move to Rust, supposedly, if we actually want to do that. if we what can and what we cannot. So the thing is that since not all architectures are supported by Rust for Linux yet, and we want to have the core components working on all the architectures, even those who may be considered legacy. So that basically includes core components, first of all, so they cannot, at this point, be Rustified. zswap cannot be Rustified. shmem cannot be. zsmalloc, well, as a matter of fact, it can be too. But maybe we want to create a spin-off, some simpler version. Maybe it could make sense. And then zram, which is not a core component, it's actually a driver. RAM disk on steroids. And it's used almost exclusively by the architectures that do have Rust for Linux support. So that makes it a good candidate. Let's see what we can make out of it. zsmalloc, going back to zsmalloc. Well, zsmalloc is tricky in the sense that it has a complex implementation, and we may want to write it in Rust and do some kind of transitional period when we have both the Rust implementation and the C implementation, and then eventually leave the Rust implementation and have the C implementation obsoleted gracefully. But the thing is that zsmalloc is actually quite huge. It's a complex implementation, and even though it's proven to work quite well with the existing conditions, it has some drawbacks, like it's not really scalable and it doesn't work that well for setups with 16K pages and bigger pages. And finally, since currently it's the only available allocator for zswap and zram, we cannot move it to Rust, but what we can do, obviously, is we can, as I said, either more or less implement it in Rust or implement something else. And that something else actually exists. There is a competing implementation, which is called zblock. And it's fairly simple in a sense that it doesn't have to inherit all the complexity that zsmalloc carries, because it's based on two simple ideas. So we use page blocks instead of single pages, and that accounts for bigger versatility of the objects of the same size that we can put into those blocks. It has comparable compression and better performance on 4K pages, and better compression and better performance on 16K pages. So there's a picture about size classes for zsmalloc. It's just illustrative. So we have very many size classes, and zblock gets away with less size classes. And X is just to make it more visible, and Y is the size in bytes. So zsmalloc divides all possible. So the idea is that zsmalloc and zblock, they both compress objects that are small from 0 basically to the page size. And so zsmalloc is dividing the space, so to say, into 255 size classes. So for 4K pages, the size classes will be 16, 32, 48, and so on and so forth. Which and then for a certain object that we see in blue, so the object in blue goes into the size class that is directly up above. So the allocated pages are divided into the same size slots, so that an object that fits in the best way goes into the certain slot. And we have many slots. With zsmalloc's case, we have a lot of slots, which on one hand produces higher granularity, but there's a problem with that that I'm going to mention slightly later. So that there are two problems with zsmalloc. The first problem, which is perfectly solvable with some performance penalty, though, is that there always will be some spillover, almost always, because the sizes of size classes do not exactly fit into one page. So there will be cases where an object will be distributed across two pages, and that has a certain performance penalty because there is a redundant copy involved in this case. And for zblock, there's no spillover because we are using some strange sizes that fit blocks of pages well. And since we use blocks of pages, then we have a lot more flexibility to fit weird size objects into those blocks. So we don't always deal with, for instance, 4K pages. We can have it in 4K, we can have it 8K, and in this case, it's actually 20. So performance comparison, it's illustrative. It's not a very serious comparison, but it's a result of a full kernel build, and with different backends, and you can see that that block is outperforming.
When I was about 15, I read a lovely little book called How to Lie with Statistics.
Sorry?
When I was about 15, I read this lovely, slender book called How to Lie with Statistics. You've got 3 of those ways on that slide that you were just on. Next slide.
This one.
Yeah. So you're not starting at 0, right? So that's the first one. So that difference, on 2 between this teeny tiny little blue and the huge, that's basically a lie. Right, you are using our visual sense to confuse all of us.
No,
you are.
I always mention this. I haven't gone through this. I always mention this. I have this slide.
Yeah, but even if you say,
but it's not me. It's the presentation.
Well, that was my second point. That you've got this weird angle going on, which really distorts how the numbers are being shown. I mean, this feels very dishonest. And you've done this with all of your slides, and I really, really hate this. You're not communicating, you're confusing.
Well, thanks for the input. Let me disagree. Okay. So it looks like on this version of the slides, I don't even have the explanation about the size classes, which I think is important. So the thing is with zsmalloc size classes is that you still have to allocate at least a page for every size class, and it's actually it may be somewhat wasteful because. For instance, you don't usually get that many objects of a size between 0 and 16. So for the size class 1, you don't really get that many. and you can actually use less size classes and have more actual allocation density, and this is what zmalloc is about, because we have more freedom to choose the classes, and actually there is an opportunity which is not yet implemented though to dynamically adjust the size classes for zblock, or well, not just, but add new size classes if that's important, if that helps the performance. So summary, not for all architectures, it's a new algorithm and seems to work pretty well. So it's implemented. There are some obstacles and there are some patches that it depends on, and submission is underway. So let's pass over to the next one. It's more of a work in progress, and this is something that I want to have more comments on, and then maybe some help. So the idea is, well, if we have the compressed RAM disk, it's basically just a virtual disk driver, and it's always good to it's almost always good to implement or re-implement that in Rust. Drivers usually go well. And besides, ZRAM has quite a bit of code that is actually not used. Well, there are some bits like for instance, right back. Maybe. I haven't seen it enabled in Android.
It's literally using billions of devices.
Well, we can take a closer look. So I would absolutely like to discuss it. Looking at the code from the configuration options that I saw on the devices that I looked closer at. I didn't see that, but I may be wrong. So let's get together and discuss.
Any other unused parts that you think are? We use pretty much everything. We don't put code that we don't use.
Well, sorry, since this is not my laptop, it's kind of cumbersome to refer to this certain code. But let's make it an open question. So I'm not holding to this statement. I believe I saw unused code. At this point, I can't prove that. But anyway. This is a big implementation, and I've seen people trying to configure it, complaining about the complexity. So the idea, I don't know, maybe it's not a viable idea, but the idea is to implement ZRAM in Rust. Using the native Rust API that will be provided by zblock, and there is certain work ongoing, but it's just a toy implementation. So at this point, there's not much to show, but the idea as such, I believe, is viable. But there may be other opinions. Finally. SHMEM. Well, as we've talked, SHMEM can't be moved to Rust because it should work on all architectures. But if it were to be moved, then the Rust DRM drivers, which is like a huge emerging initiative right now, we have. Yeah, just stop me. If there are questions, just stop me.
Yeah, I'm working on Nova, which is one of the Rust DRM drivers. I was intrigued by your talk because you were talking about moving a core thing to Rust, and so this is interesting. I would have expected the natural order of things would be first you do the Rust experiment, done, then you move and start doing things like drivers in progress, and along the way you bring up all of your CPU architectures that you reasonably care about. I mean, all of them, I guess. And then you start doing core, start changing over core things. And so this is startling to talk about core stuff before the CPU architectures are done, because you're going to double the size of your code. And so you've made things more complex. I would encourage you to direct your energy to supporting the CPU architectures and helping fix up Rust for Linux rough edges before you dive into core stuff. Just my thoughts.
Yeah, thanks. But the idea is that if we have two implementations of an allocator, for instance, that we can pick up at the compile time, then at least one of those doesn't have to support all the architectures. Does it sound reasonable?
It's reasonable to do things in parallel, yeah, it is reasonable to do things in parallel. I'm just a little concerned because I guess until we hear more about how the CPU architecture stuff is going, this is kind of, you're kind of leading things. Maybe that's okay.
Yeah, one thing I will note is that one of the things which I personally find very interesting is how much progress is happening on the GCC Rust front and back end, which should hopefully allow many more architectures to be supported because you've got the GCC backend advantages. That is a work in progress. My understanding from what I heard, and this is secondhand information, is that they were able to successfully build a kernel. It didn't work, but they were able to build it. So, small steps.
As far as I know, they can boot it as well now.
Oh, okay.
Yeah.
Oh, excellent.
All right. So the thing is, as we are talking about moving the swapping architecture in Rust, so the thing is that we can't really move shmem, but on the other hand, we've been doing quite many experiments with shmem for DRM, and well, it's fair to say that it's quite suboptimal, because what we're doing in this case is we are basically trying to swap out buffer objects, and buffer objects are in most cases quite huge, span across many pages, and we swap out buffer objects all at once because it just doesn't make any sense to have a partially swapped buffer object. So the idea is that if we can implement streaming compression for buffer objects, then we just don't need to use any special allocators at all, and that there is some prototyping on this done. So the idea is that we will just have a large compressed object which is represented by one handle, as opposed to how it's done now. Buffer objects are compressed on a page-by-page basis and swapped out on a page-by-page basis. So if there's, like, for instance, 16,000 pages in a buffer object, which is quite a normal number, it happens, for a screen with large resolution, then we have 16,000 handles, and there's a search for each and every one of them. And well, it takes quite a bit of time, and if we can avoid this and have just one single search for a buffer object, it will speed up things quite a bit. And since this is a new idea, it also makes sense to me, at least, to try prototyping it in Rust. And this is This is ongoing. So if anyone is taking interest in taking part, supporting that, it would be absolutely great. Or if there are any concerns or thoughts that it wouldn't fly for some reason, these thoughts are also very welcome. But that, I think, is basically the last slide. Thanks for your attention, and yeah, let's go into discussion if there is one.
Please speak right into
I'm trying to understand better for the page block concept you raised there. So are those pages allocated with physical contiguous address, or are these fragmented 4K pages somehow chained together?
You mean zblock?
You mentioned
it's enough to have them virtually contiguous. So basically, a vmalloc would do, and this is how it's implemented. It's using vmalloc.
So, and then in that case, the zsmalloc have do the mapping of the page list as well, right? So, is it?
Sorry, could you please repeat that? I just didn't catch it.
I'm thinking the zsmalloc are allocating individual 4K pages as well. So from the page allocation point of view, it seems not much different.
Yes, but zsmalloc does not create a virtually contiguous mapping, so it has to do a copy.
Oh, I see. So most your optimization gain is from when the object cross the boundary, and then because you don't need to do the cross-boundary copy, and then that's where the speed up come from.
Yes, that's one thing, and size classes
Okay.
is the other thing. Yes.
Hello. Do you, from my understanding, it doesn't seem like your allocator can support page migration, right? Is this something that you plan to extend, or is it already supported? I miss it somehow. Like, for example, if so the reason why zsmalloc is so complicated is because like you hand zswap just like a virtual handle, right? And then under the hood, zsmalloc can move objects around. It can like migrate the pages when it needs to like reduce the system's fragmentation. Is this something that zblock can also support, or?
I'm thinking about it, but the thing is that it's not that crucial as in zsmalloc, because zsmalloc needs that to avoid increasing fragmentation in the runtime. And for zblock, this fragmentation is not that relevant, because the worst thing that can happen is that you have somewhat many free slots, but that does not. How should I put it? That does not limit the ability to put new coming objects into these slots.
I think you confuse compaction and page migration. Mike.
I think you're confusing zsmalloc compaction and page migration. Page migration is not what zsmalloc does. It's what the upper memory management layer tells zsmalloc to do. Just tells zsmalloc, this is the new page, move the objects, free that page. Compaction is what we do in zsmalloc to battle the fragmentation, but those are different things.
Yeah, so maybe then I misunderstood the question, because if we talk about migration, then since we use vmalloc for allocation, it's basically under the hood. So we don't go into that. And if we talk about it probably is good to have it like sysfs triggered, but it doesn't have to happen in the runtime.
I'm not an expert in this algor, but general question. Did you have to use a lot of unsafe in Rust, or?
Not too much.
Oh, like
So
relatively
there are some cases you can't avoid it, but what percentage of
That doesn't matter. That's not a question. Then you always have to have someone say when you want to see it. The most hot, the most used one is unsafe.
That's not
correct.
entirely true, I
Even if
believe.
your most hot path has unsafe code on it, you don't lose the benefits of the type system. And often you will have unsafe in your most hot path because that is where you call into whatever C APIs you're calling. But what we do is we try to expose safe APIs to the drivers. Right? So typically, if you write a driver in Rust, you will probably be able to do it without any unsafe at all. That's the idea. And then the intricacies of where you have the unsafe, you wrap that in an API, a safe API that you cannot break. That's the idea. Right?
Right. So the goal, for instance, for Neo ZRAM, if it flies, so it will not have unsafe. So because the unsafe that the cases that just have to be here, they will be in the back end, but there are not that many. Like I think I have 4 throughout the code. But then again, it's not a problem per se, because for every unsafe we need to specify safety requirements and mesh these requirements. That doesn't mean that unsafe does something inherently bad. It's just it's something that we need to minimize, but at the same time it's unavoidable. And while it's unavoidable, we are working to limit the impact, so to say.
Think of unsafe as a C mode, right?
Any other questions? We have about 5 or 10 minutes. All right, if there aren't any questions, we can thank the speaker.
Thank you.